All right, friends, last example that we're going to work on together. So this one says Kermit tried to use a rope to pull his bike out of a mud puddle. The rope is pulled at an angle theta above the horizontal, but the bike does not move. So kind of similar to the hockey example with Fozzie in example 7, but a little bit different here. So let's take a look. So he's trying to pull his bike out of a mud puddle. So that's going to be our object, our system, and gravity, as as we would expect, is going to pull down. So we'll go ahead and mark that one going down. The force of the earth on the bike. And then we're going to think about what else is pulling or pushing. So it's sitting in this mud puddle. So the mud, I would imagine, kind of like the bottom of the mud puddle is pushing up on it as well. So it's got some sort of normal force or surface that's pushing up on it. We've got F of the mud, or we'll say the mud puddle, on the bike. That's going to be a normal force. Okay. And then it sounds like he's trying to pull on it. So let's go ahead and draw that force up here like this. So this is the force of Kermit on the bike. Sorry, I'm writing that kind of small. I apologize if it's hard to see. And that's pulling at an angle. So I'm going to mark that angle as theta. Now I've got these two forces. In the last example, I forgot to mention, I'm actually going to go back so you can take a peek at it here, that I intentionally didn't mark the force of the earth and the force normal as being equal. In fact, I probably should have drawn the earth force as a little bit bigger here because, as we talked about, the forces have to add up to zero, and it's not just the normal force and the gravitational force like it has been in pretty much every other problem. In this case, the two forces that are going up and down, so we've got this one here and this one here, those two have to add up to the force of gravity. So we're not, in this example, going to use the tick marks to mark them as the same length. Just wanted to clarify that. And I'm going to do the same thing on this one because, again, the Kermit is pulling up on the bike as well. That's an applied force. And so we've got some force in the, in the upward y direction here, FA y, which is FA sine theta. Okay. And that's also acting in the y direction. Similarly, we've got some x direction force, some x direction piece of that. So I'm going to go ahead and write that one out here right now. This is going to be FA in the x direction, or FA times the cosine of theta. All right, we're going to take a look and see kind of how we're doing on our questions here and determine whether or not we need some more forces. So is the bike accelerating in the y direction? I'm thinking no, and I'm really thinking no because it says that the bike does not move. If it's not moving, it's definitely not changing velocity. If it's not changing velocity, we know that the acceleration must be equal to 0. So nope, it is not accelerating in the y direction, which means that all of the forces acting in the y direction need to add up to 0. You got it. All right, so we've got F net in the y direction is going to be equal to Fn, that's pulling up, plus FA sine theta, that's the FA in the y direction, that's this one here, plus the force of gravity, or FG, and that one we're going to make sure we note is negative. So again, we said, is the object accelerating in the y direction? Indeed, it is not, which means that the net force in the y direction needs to add up to 0. Okay, in the x direction, well, it says also here that the bike does not move, which means that that's true both in the x and the y direction. That would imply then it is not accelerating in the x direction. And if we take a look at our free body diagram, looks like we need to have another force acting in the x direction to counteract that applied force. I'm thinking, given that we're trying to avoid movement or prevent motion, that the thing that might be holding it there is some sort of frictional force. The surface of the bottom of that mud puddle against the bike, right? Those two surfaces that are trying to move past one another and just are not able to. Mud is pretty sticky. So we're going to go ahead and add another force. the force of friction going back this way, okay? This is going to be the force of the mud puddle on the bike, but we'll notice that that's parallel to that surface. So that's going to be a frictional force. And then if we think carefully about this, those are the only two forces acting in the in the x direction. If they're the only two forces acting, then they have got to be the same magnitude. So I am going to mark that those two are the same. Not marking anything in the y direction because we had three forces adding up to 0 in the y direction. But in the x direction, those two are the same. So we can go ahead and say here that FA times the cosine of theta plus negative FF. I'm just saying it's negative because if we look at our little axis, we've got positive here. Friction is pulling in the other direction. So we're going to call that one negative. We're going to add those up to 0. Okay, so a couple of things there to think about, to remember. One is that we've got the rope, that tension force. I guess I wrote it as an applied force. Really, it probably should have been a tension force. Sorry about that. FT, I'm going to change those to T's. If you had it as applied, and if you leave it as applied, that's totally fine. But I'm going to go ahead and change that at an angle. And again, because it doesn't move, we know that it's not accelerating. And so we know that there's got to be something opposing that motion. And in this case, it is friction. Hope that helps. Go ahead and give those problems on that worksheet a try. I will add a solution guide for that, and we can have great conversations on Monday when I see you again. Have a great weekend, you guys.